Mr. Heffron here, and here's a video on force fields and escape velocity. Okay, so what goes up does not always come down. If an object reaches escape velocity, it will leave the planet and not fall back down to the planet. So what is the escape velocity of the Earth? Okay, so for this to work, let's say you are on the Earth and you want to launch a rocket at really high speeds. How fast does it have to go to get off the planet? So first we're going to use the law of conservation of energy. The total energy that goes in must be equal to the energy that comes out plus any heat loss. In this case, let's pretend that heat loss is negligible or zero. So the gravitational energy you have to start with, which is negative, plus your launch kinetic energy, must be equal to the final gravitational energy. So you want to be an infinite distance away so that you're not in the planet's gravity anymore. And when you get there, you want to just have escaped. If you just escape, your final velocity will be zero. So at an infinite distance, you're at zero velocity. So basically, you need to get a combined energy of zero or greater to escape. So you need your positive kinetic energy to outmatch the negative gravitational energy. And when we rearrange the formula, we get this. Your escape velocity is square root 2 times g times the mass of your planet divided by your position, which in this case is the surface of the planet, so the radius of the planet. So this is kind of cool. It doesn't matter what the mass of your object that you're launching. Your escape velocity is independent of mass. However, the more mass you have, the more kinetic energy you do need. So, the Earth has a mass of 5.98 times 10 to the 24 kilos, a radius of 6,380 kilometers. So if you launch something off the surface, like maybe from Florida, and you want it to leave the Earth and never come back, how fast do you have to launch it? So we got 2 times 6.67 times 10 to the negative 11 for the universal constant of gravity, 5.98 times 10 to the 24, that's how many kilograms the Earth has for a mass, divided by 6.38 times 10 to the 6 meters square, 6 meters, which is the radius of the Earth, and we get an escape velocity of 11,182 meters per second, or approximately 11.2 kilometers per second. So going from Barrie to Toronto in Canada, that's like a 9-second trip at that speed. And that turns out to be Mach 32.8, so almost 33 times the speed of sound. Interesting fact, the Apollo rockets were traveling at 34 times the speed of sound on their way to the moon and back. Now, also, if you compare it to a fighter plane, fighter planes, are around Mach 2. This is 16 times faster than a fighter plane. Pretty fast. So, if you try to do that in the atmosphere, you're probably going to get incinerated. So, let's compare the Earth's escape velocity to some other objects. So, for example, the Moon, where they want to make a moon base, and the largest asteroid that we know of at this time in 2020, which is 2 Pallas. So 2 Pallas has a mass of 2.108 times 10 to the 20 kilos and a radius of 272.5 kilometers. The Moon has a mass of 7.34 times 10 to the 22 kilograms, and has a radius of 1,737 kilometers. So for the Moon, if we stuck in our numbers, we get a velocity of 2,374 meters per second. If you compare that to the Earth, that's only 21.2% of the Earth's escape velocity. This is one of the reasons they want to build a moon base and build a starport on the moon. It'd just be cheaper to launch things into space later. So they think there's water there, which could be used to make rocket fuel, and there is uranium and other minerals that you could build rockets and bases out of. Although a pretty dangerous place to be. Okay, how about 2 Pallas, the largest asteroid in the solar system? That turns out to be only 314 meters per second, or 2.8% the Earth's escape velocity. So imagine trying to walk on that planet. It'd be pretty hard to do. Okay, and it's not even Mach 1, it's only Mach 0.9 to escape from that asteroid. So if you try to land on something smaller, like a meteoroid or a smaller asteroid, you may find that eventually just your jumping speed, 10 meters per second, might be more than enough to get you off that asteroid forever, which could be dangerous. Okay. How about if you're in orbit? What happens? So in orbit, you've already got some kinetic energy because you're in orbit. You got your gravitational energy, you've got your orbital kinetic energy, and you're going to have to burn some fuel or add some fuel, turn it into kinetic energy to get out of there. As it turns out, though, it's really just the same formula. The kinetic energy you need to escape, plus your gravitational energy at that point in time, has to eventually reach 0 or more for you to escape, and we get the same formula. So there you go. The only difference is r is your position in orbit, so the radius of your orbit. It's not the radius of the planet this time. We could compare the two formulas for orbital velocity and escape velocity. So if we go back to a previous video, to calculate your orbital velocity, we can use centripetal force. So in this case, it's gravity, and that is going to be equal to gm over r inside the square root. So what happened was we took the two masses of the spaceship or whatever satellite, canceled them out, the two minus signs cancel, and the r squared and the r cancel out, and we end up getting this formula. Now if we compare that to the escape velocity, you'll notice there's only one slight difference between orbital velocity and escape velocity, is there's a 2 inside the square root. Of course, if you were to square the velocity, you'd end up with twice the kinetic energy when you escape compared to your orbital velocity, which makes sense if we go back to our old binding energy formula. So the total energy in a stable orbit is equal to 1/2 your gravitational energy, which is equal to minus your kinetic energy. And so to escape, you actually have to double your kinetic energy. And to double it, you only have to multiply your velocity by √2. So there you go. So escape velocity is literally √2 times your orbital velocity. So if we take a look at a ship that's at an altitude of 1,000 kilometers above the Earth, we have the radius of the Earth, 6.38 times 10 to the 6. We add the altitude, 1 times 10 to the 6 meters, or 1,000 kilometers. And we would find your escape velocity would be 10,397 meters per second. This is definitely less than the escape velocity from the surface because you already are moving and you're already further away from the planet. Now your orbital velocity, what would it be? Well, it's pretty easy now. We have this little formula. To find your orbital velocity, just take the escape velocity, divide by √2, and we get 7,352 meters per second. Okay. Or we could do the question the other way around. We find the orbital velocity first, 7,352. Multiply that by √2, and we get the escape velocity, 10,397 meters per second. So there you go. So the orbital and escape velocities are Mach 30.5 and Mach 21.6. So now how about black holes? Black holes are fun. The escape velocity at the event horizon of a black hole is the speed of light. Hence, it's impossible to escape at that point since you would have to have no mass. Now, supposedly the minimum mass for a black hole to form is 10 solar masses. So you need a star which is 10 times more massive than our sun, and it has to run out of nuclear fuel and then collapse on itself. We want to find out where its event horizon would be. The event horizon, the radius of the black hole to that point, is called a Schwarzschild radius. Okay. So our escape velocity is going to be c, the speed of light, and we are looking for r. So what we're going to do is square both sides. So we'll get a c squared, and we'll get a 2gm over r. We rearrange that to find the Schwarzschild radius, or the radius of where your event horizon would be located, is 2 times g times m over c squared. So we're going to fill it in. So for a small black hole, like one of the smallest ones you can get, 2 times 6.67 times 10 to the negative 11. We've got 10 for 10 solar masses, and the mass of the sun is 1.99 times 10 to the 30 kilograms. and we're going to divide by the speed of light, 3 times 10 to the 8 squared. So a small black hole would only be 29,496 meters across. That's not the singularity at the middle. This is just the point of no return, where no radio signals, lasers, nothing can get past the event horizon. And that's why we don't know what the events are inside a black hole, because you could never see them. If you send a probe in there, probe's not coming back, and its messages could not come past the event horizon. So just 29.5 kilometers wide. Now let's take a look at a supergiant black hole. So at the center of our galaxy, and most spiral galaxies are giant black holes. So in this case, the biggest one that we know of is Sagittarius A, supermassive one. It's at the center of the Milky Way galaxy, and it has a radius of 1.225 times 10 to the 8 meters. It sounds big, but it's not huge. The distance between the Earth and the Sun is 1 astronomical unit. This is only 0.082 astronomical units, or 8.2% of the distance between the Earth and the Sun. Even Mercury is further from the Sun than that. So, to find the mass of this supergiant black hole, we're just going to take our equation, rearrange it. So the mass is going to be the radius times the speed of light squared divided by 2g. And the size of this black hole, 8.26 times 10 to the 36 kilograms, which is 4.153 times 10 to the 6 times more massive than our Sun, which has a mass of 1.99 times 10 to the 30. So this black hole is huge. It's 4.153 million times more massive than our Sun. So just imagine our Sun, multiply the mass by over 4 million. That's the supergiant black hole. Huge. Crazy. So it's like the mass of our solar system times 4 million. It's insane. So, there you go. Some interesting information for you. So, the escape velocity is the speed or velocity needed to escape from a gravity well or force field. And this is when the old adage, what goes up must come down, finally fails to be true. And so the useful formulas here, here's escape velocity, square root of 2gm over r. If you're in ground or orbit, doesn't matter. If you want to compare escape velocity to orbital velocity, your escape velocity is root 2 times the orbital velocity. And if you are interested in black holes, the Schwarzschild radius, where you find the edge of the event horizon, is 2gm over c squared. There you go. So this is one of the ideas right here, a giant electromagnetic railgun to shoot spaceships into space. So if you can get the ship up to the right speed, it would never come back to the Earth. There you go. Hope this helps.